Good morning and welcome back. Today we will talk about center phase linear antenna. This is the last section of chapter 9. Actually, last semester, sorry, last Tuesday, we talk about part of the center phase linear antenna. We talk about 36 to 40, and today we still have 5 pages to go, 41 to 45. Since we still have time, I will take this opportunity to review what we have learned. So when you learn the new material, you will have a better understanding. Okay, so let me say that again. Center phase linear antenna. Uh, this is a qualitative look at the center phase linear antenna. Center phase, that is feed at the center. This is the center of the antenna. And how to feed this center? We use a current source. So this is something looks like transformer. We have C and R, so it's an RLC circuit. It's a resonator. Energy will transform from here to LC circuit and then convert to here. And this will energy will transmitted through the transmission line. So current will be AC current in this direction or in this direction. Okay. Or on the other hand, in this direction and this direction. So it's a center phase linear antenna. And this antenna will generate radiation. So you can imagine in the near run, current will flow in this direction or in this direction, oscillating sinusoidal current source. And this from the magnetic field, if we have a changing current source, we will generate magnetic field in this direction or in this direction, opposite direction, clockwise or counterclockwise. Okay, so look at the electric field. Because current flow in this direction, so we will have positive charge here and negative charge here. Electric field starts from positive charge and terminates at negative charge. So electric field is in this direction, magnetic field in this direction. And if we change the current, electric field might be in this direction. Okay, so at far wrong, electric field is in perpendicular, basically in the z direction. In this direction, in the z direction, and magnetic field will be in this direction. So E cross B will give us propagating wave. In the near run, E and B are principally generated by rho and J respectively. However, this is near run is basically is a static field patterns. In the far run, E field and B field are regenerative through. This is Ampere's law with Maxwell correction. This is Faraday's law. Partial B, partial T, partial E, partial T. So E generate B, B generate E. We call regenerative. Okay. This is a detailed analysis of the center phase linear antenna. We like center phase linear antenna because it's easy to calculate and we will obtain a closed form of the solutions. Besides, this is correct for any value of KD. K is wavelength, wave numbers, 2 pi over lambda. And D is the physical dimension of the antenna. Okay, so KD 1 over D 1 over d, 1 over d, 1 over d. So the physical dimension is d. So, however, in previous two chapter sections, section 9.2 and 9.3, we make such assumption. KD is very, very small, but here we don't have to do that. Yes, we will do that later, but not now. So A vector potential mu 0 over 4 pi d3 x prime exponential ik x minus x prime divided by x minus x prime times the current source in terms of x prime, where the current source is written in this form. This is a reasonable assumption because look at x direction, y direction. Current source is in the z directions. So we can consider the antenna is ultra thin. So only in the x direction, x equals 0 and y equals 0, we have value. Otherwise, nothing. And another assumption is not assumption, reasonable assumption is here. At this point, z equals d over 2. Z equals d over 2. This one is 0. Sine 0 give us 0. So no current here. Reasonable because it's an open end. It's a termination. And on the other hand, when z equals minus d over 2, we have another 0. 0, 0. Okay? And it's sinusoidal. It not necessarily be a sinusoidal, but sinusoidal looks reasonable. Okay? Therefore, I say it's reasonable assumption. With this one, with this assumption, we can calculate everything. The vector potentials, EZ move to here, mu 0 I, I move to here, mu 0 E 4 pi here. The integrations from minus d over 2 to plus d over 2, the z prime, and integrate over z. Where is the s and y? S and y give us 0 and 0. Okay, we are going to calculate this one. With this one, with the vector potential, we can calculate magnetic field. And we can calculate electric field. We got everything. We got Poynting vector. We got energy density. We can obtain everything. Note that J is symmetric about Z equals 0. So Jz equals J minus Z. Symmetry. Second, I is the peak current only when Kd greater than pi. When Kd is greater than pi, we have signed pi over 2. Okay, that's maximum value. So I is the peak current in this case. The antenna appears to be an open circuit. Open. In that case, there should be no current flow, but don't forget we have a changing AC field, changing electric field and changing magnetic field. So it's okay. So go back to this one. Next step, we can consider this one and this one. Okay, this one can be read into r squared minus r prime cosine theta. R is here, absolute value of x. R prime is the absolute value of x prime. Okay, theta is the angle between x prime and x. Okay, So we just align the dipole in the z-axis. Therefore, their angle is theta. In the previous case, we say gamma. It depends on theta prime, theta, phi prime, phi. But here, we just align the source in the z direction, so we got only one term, theta. R prime is normally small. R is much larger. So we can move R to outside. So we can have this one. Here, let me show you a Taylor expansion. Taylor series. Taylor series give us, this one will give us 1 minus 1 minus 1 over 2x minus 1 over 8 squared, and so on. So first one give us this one. Second give us this one. Okay. For the R dependence, we got only one terms, R, and 1 over R dependence. Once again, we got 1 over R because of R, and we have 2 here. We have 2 in the numerator and 2 in the denominator. Cancel. So we have minus n dot x prime. And next step, minus, so we have plus R, R, so we have 2R, R prime square, and another one, 1 over A, 1 over A square, so it's 4, so it's 1 over 2 here, and we have a minus sign, so it's n dot x prime square. Here is R square, but because of R, so we can move to the front. Okay? So actually, to the first order, we can write the absolute value of x minus x prime is approximately equal R minus n dot x prime if the observer is much greater than the source. That is in this case. Hence, when R is much larger than D, we can rewrite this one equals approximately equal R minus G prime cosine theta. Okay? And substitute this one into the integrations. We got this one. Say an exponential minus ikz prime cosine theta, and here R minus G prime cosine theta. Okay? And it's still not that easy. But remember, not here. G cosine theta in the denominator can be neglected because R is much larger. So Z prime cosine theta plays a minor role in the denominator. However, in the exponential terms, let's make an important contribution to the phase angle even at R greater than D. Okay, so these terms, exponential terms, are very important. However, this term is not very critical, so we can simplify into R, move to the front here, 4 pi Ez mu 0 I exponential ikr. Okay, what else? And we say that exponential minus ikz prime cosine theta, because this one is small. This one can be rewrite into this one after integrations. Once again, this can be considered as extra bonus from equation 9.54 to equation 9.55. You need to use integration by parts. but that is relatively easy. You can do it by yourself. And just consider it as an extra bonus. You can write it down and send your answer to me. You will got 1 point in total score, in the overall score. So 1 point. Therefore, calculate this one. We have this result. Okay, next one. Okay, so in the far wrong, we can write into this one. Pointing vector per study angle, time average, 1/2, take the real part, 1/2 because it's time average, r squared, n dot e cross h, this is pointing vector, and per study angle. E is related to h through these relations. By doing so, we can, it's a triple product, h cross n cross h complex conjugate. So we got one terms here eventually, n h cross h star. So we have z0/2 r squared h absolute value square. How to calculate h? H is related to 1/mu0 curl of A. So we have Z0 here, 2 here, mu0 square. And this one gives us IKN cross A. And we got A over there in the previous page. So we got K square, R square, sine theta square, A square. So all we need to do is put A square, this one, A square. A square, we have sine to the fourth. So after operation, we have sine square in the numerator, and this turns in the sine square in the denominator, cosine kd/2 times cosine theta minus cosine kd/2 in the numerator. Okay, it's a closed form. It's valid for r greater than d and any kd. Also, it's independent of length. Of course, lambda should be greater than d, and observer is much greater than d. Okay, let's consider two special cases. One is kd equals pi. Kd equals pi. We have pi/2. But remember, this one, pi/2 cosine theta. We have trigonometric identity. We can simplify this one into this one. Coefficient the same, but this one can be pi/2. So this one give us nothing. Nothing here is 0. So we have pi/2 cosine theta square sine square. Okay, that's for pi. On the other hand, we have kd equals 2 pi. Equals 2 pi, this is minus 1, so it becomes plus 1. Plus 1. And we have pi here. Pi cosine theta. Cosine pi cosine theta plus 1 can be rewrite into here. Okay? Sine square. The first condition is called half wave antenna. Kd equals pi means lambda equals 2d. D equals pi over lambda over 2. So it's a half-wave antenna. On the other hand, KD equals 2 pi, lambda equals D. That's full wave antenna. D equals lambda. D equals lambda over 2. So it looks like a superposition of two half-wave antenna excited in phase. What's the difference? If we have this one, the angle is much broader. However, for this one, it's quite sensitive to theta, so it will become narrower. So very coherent, less coherent outside, and very coherent at theta equals pi over 2. We have a narrower beam width. So actually this one gives us the idea of phase array radar. By control the phase here, we can control the beam profile, beam directions. Okay, next one. So let me write it again. This is the equation 9.56 without any approximation, without two special case, no special case. But we will consider the limiting case. That's dipole approximation. That is KD is smaller than 1. We don't have to make this assumption until now. Just consider wavelength is much greater than the physical dimension of the dipole. So cosine theta, very small, cosine x equals 1 minus s squared over 2 for this case. Because this one is small, so this one is very small. Cosine KD over 2, we can write into this form. And this is very small, so we just write into here. Therefore, pointing vector per solid angle time average z0 I square over a pi square 1 minus k square d square over a cosine theta square minus 1 plus kd square k square d square over 8. So this one cancel. So we have this one k squared d squared over 8 move to the front. A times 64. A times 64, we have 512. Z 0 I squared over pi squared. And here we have k squared d squared. Okay, kd to the fourth. And 1 minus cosine theta. So it's a sine theta square. Because cancel, we have sine theta in the absolute value. So it's sine theta square. This is valid for KD smaller than 1, this case. And this one is valid for any value of KD. So this has the same KD and theta dependence as in section 9.2 electric dipole, which was derived by assuming KD smaller than 1. Okay, we just double check everything. Okay, we can discuss something called radiation resistance and equivalent circuit. This is the radiation, and because this one KD is very small. So we can, once again, we can write into this one, sinusoidal KD, so 2 pi over D. The current can be simplified into this form. And in a previous page, we know the power per solid angle time average gives us this one. So I square, we have I square. I0, we say this is the peak current, the highest current. Highest current is Z equals 0. Okay, let's correspond to highest current. This time the highest current is not I, but KD over 2 times I. That's the highest value. We say peak current. So you might expect I is the peak current, but it's not because KD over 2 is small. So I0, we just define the peak current. Remember, we said if KD over 2 is greater than pi, then I is the peak current. But in this case, KD over 2 is very small, so we need to multiply. So I0 we call peak current. So in that case, we can rewrite this one. KD we can rewrite divided by 4. So I0 square. So this is the peak current, 2 pi 128 pi square, KD square, sine square, theta square. Okay, so we can perform uh, calculate total power averaged. We To calculate the total power, we need to consider the solid angle, including in phi direction we have 0 to 2 pi. In theta direction we have 0 to pi. In terms of cosine theta, we have -1 to 1. Okay. So in terms of cosine theta, this is sine theta squared. So we can rewrite into x minus 1 minus x squared x. So eventually we got this one. This gives us 2 pi. And this one we can simplify. So eventually coefficient z0 I square pi square, because this one gives us 2 pi cancel. And we have kd square. So we got this one. Z0 I0 square over 48 pi kd square. So power can be write into this form. Current square over 2 times R. So R can be considered as radiation resistance. RAD, the subscript just indicate it's a radiation resistance. The power will radiate, just like the energy will become smaller. So just like energy consumption, just like this one, incident energy, incident current, voltage, and it will radiate. Okay? See second terms. Okay, so we can write into an equivalent circuit for a center fed antenna. This one, Z0 is 377 for the vacuum. 377 divided by 24 pi, 3.14. So eventually we got roughly about 5 kd square. We know kd is small, so radiation is actually, the ohm is quite small here. So you can expect radiation, we have low or radiation resistance. Okay, let's move on. We still have 4 pages. Actually, we will consider the problems. Problems 9.16 and 9.17. 16 and 17. First, let's consider the simplest case. We have 3 problems. 1, 2, 3. 1. The full wave antenna radiation in equation 9.57 can be thought of as the superposition of 2 half-wave antennas. 1. Superposition of 2 half-wave antennas, one above the other. Half-wave antenna, one above the other. Excited in phase. That's full wave antenna, just like 2 half-wave antenna. Demonstrate this by rederiving dp over d omega for a full wave antenna by superpositioning the fields of 2 half-wave antenna, each of wavelength d over 2. So if we want to calculate a full wave antenna, it can be synthesized as a 2 half-wave antenna. Okay, how to do that? First, the principle of superposition requires that we add the fields, not the power, of the 2 antenna. Keep this in mind, the fields, not the power. Okay, if you use power, that's incorrect. Each of total length d over 2. So we have the first one. This is the original form. But now it slightly shift. One shift to here, the other shift to here. Okay, so R will be different and theta will be different, but actually it's still the same. Equation 9.55 applies to a single antenna of total length d. Okay, so the field of each of the 2 antenna in this problem can be obtained by equation 9.55 by replacing d into d over 2. Okay, remember this half wavelength. This is full wavelength. So we must simplify. We must replace d with d over 2 and express r with respect to r1 and r2 because the center is shift to here. Upshift, downshift. Okay, so A12 is easy, mu 0, I exponential ik r1, r1, r2, 2 pi over k, r12, r1, r2, and d is, the new d is this one. So kd over 4, cosine kd over 4, the same. And r1 is r minus d over 4. R1 is minus d over 4 cosine theta. R2 is minus d over 4 r plus d over 4 cosine theta. Okay, and substitute these two into here. We may approximate R12 in the denominator of phi by R. Just approximate this one, but must use the correct R12 for the phase angle. Correct R12 for the phase angle. This one, once again, in the denominator, we can approximate as R. Doesn't matter. But here, we cannot do that. We must be careful. We talked about this idea before. So it's assumed that each antenna in this problem is excited in half-wave patterns. Hence, we set KD/2 equals pi. Okay, simplify the calculation. In phi, KD/2 equals pi. So exponential IKR, no change, mu 0, I, no change. And we have two extra terms. We have two extra terms here. One is minus I over pi over 2 cosine theta plus exponential I pi over 2 cosine theta. And what else? This one, KD/2 equals pi. So it's pi over 2. So this one is 0. Okay, good. So we have only one terms. Cosine pi over 2 times cosine theta, sine theta square. Okay? And this one gives us a cosine. This one, exactly the same. 2 cosine pi over 2 cosine theta. So we have 2 cancel with this one. So we have easy mu 0 pi I kr exponential ikr cosine pi over 2 cosine theta. Cosine pi over 2 cosine theta. Okay, sine square theta. So the starting angle AP is proportional to A squared. Therefore, the result will be this one. Okay, the same, exactly the same as the full wave solution in equation 9.57. Exactly the same. If you don't believe, this one. See? For uh, for full wave antenna, this one, this one. So exactly the same. Exactly the same. Okay, let's have a look at problem 2. If the two half-wave antenna in problem 1 are excited 180 degree out of phase, that is one in this direction, the other in this direction, current is opposite, derive that dp over d omega again by the method of superposition. Okay, let's calculate the vector potential first. If the two half-wave antenna in problem 1 are excited 180 degree out of phase, we simply replace the plus signs with the minus sign. Okay, with the plus sign with the minus sign here. So it becomes sine. This one becomes sine, sinusoidal. sine pi over 2 cosine theta over theta. And this one, and we have minus I here, minus I. Okay, others are similar, sine theta square, coefficient the same. We have minus I, we have sine pi. This one can be rewrite into it's not finished yet. And we just substitute this one into here. z0 over 2 mu 0 square k square r square sine theta square. Okay, sine theta square can cancel with this one, but this one we have a square, so we got still sine theta square in the denominator, and I square mu square because of this one cancel with this one. Z0 here, Z0, 2 pi square, kr square cancel, and absolute value give us nothing. So we still have one terms, this square times this square, and this one give us divided by 4 becomes 8. 4 sine square cosine square. So this one becomes sine pi cosine theta square. Okay, look at becomes this form. Okay, go back to problem 3. Problem 3, plot the approximate angular distribution of dp over d omega in problem 1 and problem 2, in phase and out of phase, and explain the difference qualitatively. Draw the approximate, not exact. So just use your hand to draw these figures. So this one, let's draw this one first. So cosine theta equals 0. Cosine theta equals 0. This one is this one will be very small. So just draw these figures. This one we already know. However, for theta equals pi over 2, this is 0, 0, 0. So here we have nothing. Yeah, theta equals pi over 2, we have nothing, unlike this one. And theta equals 0. Theta equals 0, we have 1. But sine pi give us 0. Okay, so theta very small give us 0. Theta very large, pi. Okay, theta very pi, this is 0. This is 1. 1 pi or minus 1 pi. Once again, 0. And this is not 0. Sine pi divided by sine pi. So very small. If this one argument is very small, so we can argument very small. Argument very small. Sine theta over cosine theta. Okay. So at least here 0, 0, and here 0. So we expect the maxima will be here and here. This is the ideal, similar to the phase array radar. If two antennas are in phase, then in the center, will be the largest. It's a dipole radiations. If the two antenna are out of phase, one in this direction, the other in this direction, then it looks like a quadrupole radiations, and the radiation will become very small in these directions. How do a phase array antenna? So if we have a phase array 2 by 2 or 10 by 10, we can control their phase delay. So we can control the direction of the array easily, and we can control the phase. We can sweep the beam. It looks like a search beam, but you don't have to change the position. All you need to do is change the phase. Then you can synthesize. For example, one is here, the other is 10 degrees, so you can sweep this one. Okay, that's the idea of phase array radar. Okay, we still have 8 questions. Our TA also upload the solution guide to the YouTube, so you can study by yourself. Remote learning is convenient, but it's personally I like to stay in the classroom face to you, so I can see your response in time. I can answer your questions. So I don't really like remote learning, but because of the novel coronavirus, we should uh, avoid contagious. We can minimize the infection of novel coronavirus. Therefore, we will still use this master. We will still use this master. Okay. I will tell you uh, how to conduct our midterm exam. Probably will be take-home exam and open book. Probably. Okay. Because we have pretty good progress. So we can stop here. I will invite you to ask questions during our office hour. During our office hour. During our office hour, you are invited to my office and discuss with me. Just remember to put your face mask on. Put on your face mask. Then you are welcome. Okay, that's it. See you next time. Next time we will talk about chapter 10. Bye bye.